Hello and welcome to the discussion on the muscular system. As we go over the muscular system, we're going to be looking at several different things. We're going to start off looking at resting membrane potential, which should be a review from chapter 4. We're going to look at the gross and microscopic anatomy of muscles. We're going to talk about the physiology of excitation-contraction coupling. We're going to look at how muscles obtain and use energy, what happens to muscles as we exercise, and what happens to muscles as we get older. Now, going back and reviewing the plasma membrane a little bit, remember it's a phospholipid bilayer, so there's two layers of the phospholipids. The heads of the phospholipids have polar regions, so they are hydrophilic. They get along with water because water is also polar and has a charge. Meanwhile, in the center of the plasma membrane, we have the fatty acid tails, which is a hydrophobic region. Things that are nonpolar are just fine with the center of the plasma membrane, but things that are polar or that have a charge or that are hydrophilic really don't like to go through the middle of the plasma membrane where we have all those fatty acids. This makes the plasma membrane very effective for separating water inside the cell from any kind of water outside of the cell. Now, to get things that are hydrophilic or have a charge or that are polar through the cell membrane, we're going to need some kind of gateway or door to get them through because they can't just go through the plasma membrane. We're going to use transport proteins. These can be channels or carrier proteins. They could be pumps, which use ATP, symporters, which will transport more than one thing at a time in the same direction, and antiporters, which will transport two things in opposite directions. Remember, the plasma membrane serves as a physical barrier between the fluid inside of the cell and the fluid outside of the cell, which we call interstitial fluid. And it regulates the movement of things into and out of the cell. Things don't get to wander in and out. It is selectively permeable. When we look at membrane transport, we can basically divide everything into two categories that would be passive processes and active processes. Remember that passive processes are driven by the propensity of the universe to spread everything out. Entropy increases, and so if you take anything and concentrate it in one area and then let the universe have its way with it, it's going to spread out until you have about the same amount of that substance anywhere you look. Active processes, on the other hand, require local energy use, and in the body that's in the form of ATP. But this allows us to work backwards and concentrate things in a certain area. So diffusion is that net movement of a substance from an area of high concentration to an area of lower concentration. Molecules and ions are constantly moving. They're kind of doing a little jitterbug or a mosh pit, and that's due to kinetic energy. If we don't stop the diffusion, then the diffusion of these molecules will continue until they're equally distributed throughout the region, and that is called equilibrium. If a molecule is allowed to go through a membrane, then we can look at transport. If it is fat-soluble or non-polar, then it can passively diffuse right through the membrane. It does not need a gateway. It can make it through that middle region of those hydrophobic tails of the phospholipids. If it's ionic or has a charge or is polar, then we're going to need that little gateway. And so we can use different protein transporter molecules. We've got carrier molecules and channel molecules. So if we're going to use a channel molecule, we call that channel-mediated facilitated diffusion. And the channels can either be continuously open, which means that the molecules in question can diffuse back and forth across the membrane as entropy drives them. Or they can be gated membranes, meaning that the molecules cannot pass through the proteins unless the gate is open. Usually the gate is shut, and we're only going to open it when certain things happen, and that allows us to control the flow of these ions into or out of the cell. And then we've got active processes like the sodium-potassium pump. It's an ion exchange pump. It's a antiporter. So we're going to spend 1 ATP, and that's going to allow us to push 3 sodium out of the cell and 2 potassium ions into the cell. It keeps doing this again and again and again, and we can move against our concentration gradient, but we have to spend energy to do this. Finally, there's exocytosis, which we're really not going to get into here. Remember, it is a bigger transport process across the cell membrane. And finally, resting membrane potential. As the membrane sits there and the sodium-potassium pump goes along, it never ever stops. It continues for as long as you're alive and for quite a while afterward. And it keeps putting sodium out of the cell and pushing potassium into the cell. And what this does is it gives us kind of an imbalance. Since we're pushing 3 sodium out and 2 potassium in, both sodium and potassium are positively charged ions. But since we're moving 3 out and 2 in, that means every time the pump runs, we have an extra positively charged ion outside of the cell. Or another way to look at it is that we have one less positively charged ion inside of the cell. So as the sodium-potassium pump keeps on going on the cell membrane, and remember, there's hundreds or thousands of these on every cell, it's going to start to build up a charge, meaning that in any local area of the membrane that you measure, we're going to have a lot more positively charged ions outside the cell and a lot less positively charged ions inside of the cell. In essence, we can say that the inside is negative relative to the outside. And this is what we call resting membrane potential. Because we have that unequal distribution of our sodium and our potassium, these ions cannot move across the membrane through diffusion, because any kind of channel has a gate, and the gate is currently closed. So as the pump works, we're pushing the sodium out, and the universe would love to even the sodium out, but it can't, because there's no doorway. There's no open doorway or open gate for the sodium to move. And the same with the potassium. We've got a huge concentration of potassium inside of the cell and a low concentration outside, and so the universe would love to move some of those potassium ions out of the cell, but again, it's not allowed to because there is no open gateway. Here's an example of our sodium-potassium pump. This right here is a channel protein. You can see that molecules can go straight up and down the middle there, and there's no gate on it. Here is a pump. It's our sodium-potassium pump. We've got room on the inside for 3 sodium ions, and then room on the outside for 2 potassium ions. And so we're going to move 3 sodium out and 2 potassium in. Every time that single molecule there cycles, it's going to keep doing that. So when we look at maintaining the resting membrane potential, we're going to look a lot at sodium and potassium, as I've already mentioned. We call it resting membrane potential because when the cell is at its default state, what we would call resting, we're establishing and maintaining this potential. I know the cell has to work and spend ATP to maintain resting membrane potential, which sounds kind of weird that we have to spend energy to rest. But if there is no potential energy, if there's nothing moving across the membrane, or the ability for things to move across the membrane, if there's no potential, then the cell is dead. And so we don't ever want to reach that state with the cell. Potassium is the most important ion when we talk about resting membrane potential. It tends to leak out of the cell. And because of that, we're going to go ahead and be able to pump it back in. And to do that, we can keep pumping the sodium out. Sodium is going to diffuse into the cell and will enter through sodium leak channels and go down a concentration gradient, of course. But the leak channels prevent as much sodium as they do the potassium leaving. So that's going to help establish our resting membrane potential. So as the sodium-potassium pump keeps on kicking around, we're going to pump 3 sodium out and 2 potassium in. Remember, they're going in opposite directions against their concentration gradient because we're spending energy to do this. And remember, we're putting one less positively charged ion into the cell, making the membrane negative. Let's see if I can draw this fast enough. Here's our cell membrane. If we have 3 sodium out and we've got 2 potassium inside the cell, do you see how we've got one less on the inside, so we could call that -1. But since the sodium-potassium pump keeps on going and going and going, we're going to hit a relative number of anywhere from -70 to -90. And we can measure the potential energy on the membrane in a measurement called a volt. Perhaps you've seen your little square batteries that go inside smoke detectors. These are 9-volt batteries. That's a measure of the electrical potential energy that should be stored in the battery. On our cell membranes, we're at about -70 to -90 millivolts. So quite a lot less than your typical 9-volt, but there's still electrical potential on the cell.